Hello everyone, welcome to the 15th tutorial class on digital communication. Now coming to the content, in this class we will discuss about the quadrature phase shift keying type of digital modulation. Apart from the waveform of QPSK, we shall also observe different generation and detection technique of QPSK, and at the end we shall observe the spectrum of the QPSK and we shall calculate the corresponding bandwidth for the QPSK. Now coming to the introduction to the quadrature phase shift keying QPSK digital modulation. Now, uh, in case of ASK, BPSK or BFSK, we have used only one bit as one symbol. Now, if you want to increase the bit rate, it is possible to divide the incoming data stream into a group of two or more bits. And now each group can be represented by a specific value of amplitude or phase or frequency. This process is basically known as the multi-level modulation. Okay, QPSK is an example of such kind of multi-level modulation. Okay, now the full form of QPSK is quadrature phase shift keying. Quadrature, quad means four. Okay, so in case of quad QPSK, two successive bits are grouped together, and these two successive bits, after grouping, they make a message. Okay, now each message can be represented by a distinct value of phase shift of carrier. Okay, as BPSK, in case of BPSK, for 1 there is no phase shift, and for 0 there is biphase shift. However, in case of QPSK, what we have done, we took two successive bits, make group of them, and for each of the group we assign a different phase shift for the carrier. Here you can see that if we select only 2 bit, that means for the incoming bit 0 and 1 is possible. So for selecting only 2 bit, 4 combination is possible: 0 0 0 1 1 0 and 1 1. So by making two successive bit as one symbol, so 0 0 can be considered as one symbol, 0 1 can be considered as the second symbol, 1 0 can be considered as the third symbol, and 1 1 is considered as the fourth symbol. Here you can also observe that for individual incoming bit the duration is TB. However, in case of QPSK, the total time duration will be 2 TB, as we consider two successive bit for a one symbol. Okay, so here you can it is written that note that every symbol consists of 2 bits. Okay, now for conventional QPSK, for message 0 0 0 1 1 0 and 1 1, the corresponding phase shift, initial phase shift or phase angle, will be 0, 90 degree, 180 degree and 270 degree respectively. Okay, so here you can see that the course it is the bit sequence for 0 0, the phase shift is 0. Okay, so for the corresponding QPSK will be look like this. If we consider cos omega ct, sorry, if we consider sin omega ct or sinusoidal signal as the carrier signal, so for 0 0, as the phase angle is 0, initial phase is 0, so obviously it will start from the 0 point and it will continue up to the next interval. Okay, now for the second message or second symbol for 0 1, okay, the phase shift is 90 degree. So whenever the phase shift is 90 degree, that means sine is converted into cosine. That means it will start from +1 and it will go to the downward direction. Okay, so the next for the next symbol or next message, the carriers will begin from this. Okay, and it will continue up to this interval. Now for 1 0, it has been written that 180, that means 180 means sine 180 means that, then that means -1. So the next bit will be starting from the this point. Okay, so you can see that when the phase is 0, it will start from 0 to upward direction, but in this case it will start from 0 but negative direction. So it will continue up to this point, and whenever it is 270 degree, that means it will start from -1 and it will go to the upward direction. Okay, so like this it will continue. So this is the conventional waveform of the QPSK, where for 00, 01, 10 and 11, corresponding phase shift are 0, 90, 180 and 270 degree. As there is four combination is possible, that's why we call it as 4 PSK or quadrature PSK. Okay, and okay, now this is the you can say that this is the conventional signal space diagram or constellation diagram for the QPSK. So you can see that this one is the 00 position, this one is the 01, 10 and 11, as there are 90-degree phase difference, so obviously the angle between them will be 90 degree. Okay, so this one is the waveform for the QPSK. Now, alternative approach. An alternative representation for QPSK is very popular, which is also known as the pi by 4 QPSK. Here, instead of using 0, 90 degree, 180 and 270 degree phase shift, we have used pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4 radian for the different symbol. So the corresponding phase shift for the symbols are given here. So for the first symbol, which can be represented by 10, the corresponding phase shift is pi by 4. Remember this combination. Second symbol is 00, and the corresponding phase shift is 3 pi by 4. Third combination, that is 01, which is 5 pi by 4, and fourth one is the 11, that is 7 pi by 4. Why it is written in this orientation, it can be explained later. Okay, so right now just remember, for 10 corresponding phase shift is pi by 4, for 00 corresponding phase shift is 3 pi by 4, for 01 this is pi by 4, and for 11 7 pi by 4. Okay, now coming to the mathematical representation of QPSK, or you can call it as pi by 4 QPSK. Okay, so QPSK signal can be represented mathematically as under using this mathematical equation. So V QPSK T can be represented by A cos omega ct plus 2m plus 1 into pi by 4, where m equal to 0, 1, 2, 3. And if we substitute p equal to a square by 2, then obviously it can be written as root 2 ps cos omega ct plus 2m plus 1 pi by 4. Okay, now m is a constant and that is depending on the defined symbol. That means for the defined value of m, we can get defined message. Okay, so for m equal to 0, we get the symbol 1 s1. So the equation for the symbol 1 or message 1 is the root 2 ps cos omega ct pi by 4 if you substitute m equal to 0. So for m equal to 1, corresponding equation will be for the message, second message. Okay, that is root 2 ps cos omega ct plus 3 pi by 4. And similarly for s3 it will be 5 pi by 4, and for s4 that is 7 pi by 4 for m equal to 2 and 3 respectively. So that is the mathematical equation for the QPSK. Now we want to calculate, or we want to draw the signal space representation or signal space diagram for the QPSK. So from the earlier description, we already know that QPSK can be expressed in terms of this equation: root 2 ps into cos omega ct plus 2m plus 1 into pi by 4, where m equal to 0, 1, 2 and 3. Now, as you already know, by using the trigonometric rule, cos a plus b equal to cos a into cos b minus sin a into sin b. So this can be expressed like this. So root 2 into ps cos omega ct into cos 2m plus 1 into pi by 4 minus root 2 ps sin omega ct into sin 2m plus 1 pi by 4. Okay. So now, as we want to draw the signal space diagram, so obviously we have to express in term of energy. So as we want to express in term of energy, so as we know, the relationship between energy and power is ps into ts equal to es. That means energy equal to power into time period. So just what we have done, just we have multiply ts, that is period or interval, uh, multiply and divide both numerator and denominator of all equation, like ts into ps, and we divided it here as 2 by ts. Okay, so we expressed this equation like this way: ts into ps cos 2m plus 1 pi by 4 into root 2 by ts into cos omega ct minus ts into ps sin 2m plus 1 pi by 4 into root 2 by ts sin omega ct. Okay. Now let us assume that root 2 cos 2m plus 1 pi by 4, that means this section cos 2m plus 1 into pi by 4, this is BET. We can call it as even signal also. And root 2 into sin 2m plus 1 pi by 4 at BOT, that is odd signal also. Moreover, whenever we want to draw single space diagram, we need two orthonormal basis function or carrier function. So here you can see that this one is a carrier cos omega ct. Here you can see that there are two carrier, but although they have the same frequency, but they have phase difference. So one is and they are perpendicular to each other. So one orthonormal basis function will be related with the cos omega ct and another will be sin omega ct. So we can write, or we can assume that one orthonormal function like this, root 2 into 2 by ts cos omega ct, and another orthonormal function phi t2 or u2t equal to root 2 by ts into sin omega ct. Now substituting all this, that means BET, BOT, UT and U2T into the previous equation, and we get this kind of equation. What is that? That is VQPSK T equal to root TS into PS multiplied by 1 by root 2 BET into U1T plus root over TS into PS multiplied by 1 by root 2 into B0T or BOT multiplied by U2T. Okay. So in the generation of QPSK, U1 and U2, sorry, yeah, U1T and U22 are used are as carrier. Okay. Now, as you already know that in case of QPSK, TS equal to 2 TB. That means for only one symbol, two time period for one bit, or period for one bit has been used. Okay. So you can write Ts equal to 2 TB. So by substituting this into this equation, you can write root TB into PS 1 by root 2 BET into U1T, root 2 TB into PS 1 by root 2 BOT into U2T. Now, as we know, TB into PS equal to energy per bit. So obviously you can write like this, root over EB into BET into U1T plus root over EB into BOT or B into UTT. Okay. Now, if you use polar energized line coding, where 1 is represented by plus 1 and 0 is represented by minus 1. So for 0 1, for 0 1, first bit is odd and second bit is even. So as for polar energy, 0 can be represented by minus 1 and 1 is represented by 1. So 0 1 can be given by like this, minus 1 1 0 0, that means both are minus 1, 1 0 plus 1 0 is minus 1, 1 1 both are plus 1. So for this case we can easily define QPS equation for the QPSK for the each of the symbol, and for the respective symbol the corresponding equation are given by like this. Like for minus 1 1, the first part is minus PS and second one will be plus. This one is both are minus minus, that means this one is the minus PS, this one is also plus minus PS, this one is the plus, this one is the minus 1. So this one is the root plus plus root PS, root over PS, and this one is the minus root over PS. And for the 1 1, both are plus 1, that means both are plus PS and plus root PS. Okay. And in this case, if we draw the corresponding signal space diagram, okay, so for first message will remain in the first quadrant, it will remain in the second, it will in the third, and it will be in the fourth. Okay, first quadrant, second quadrant, third and fourth. Okay, so Above equation, this equation can be used, or this table can be used for the plot of the signal space diagram of QPSK, okay, where u1 and u2, u1t and u2t can be used as the respective reference axis for the orthonormal basis function, where both are perpendicular each other. But it is interesting to note that uh, we should uh, we should observe the polarity of u2t along the vertical axis. Now let's see. So this one is the signal space diagram for the QPSK. Okay, so along this axis we consider u1t, and along this axis we consider u2t. Okay, but it is interesting to note that in this direction u1t is positive, in this direction it is negative. But however, in case of single space diagram, in the upward direction we consider the negative, in the and the in downward direction we consider the positive u22. That's why, that means fourth coordinate can be considered as the 1 1, that means where both are positive. And this coordinate is can be considered as the where bet is minus 1 and bot is minus 1 and bet is the plus 1. Here both are negative, you can see that u1 are negative, u2 negative. And here you can see that u1 is negative but u2t is positive. So here bot is 1 and bet is minus 1. So obviously it is that's why it is corresponding to 1 0, this is corresponding to 1 1, this is corresponding to 0 1, and this is corresponding to 0 0. Now as the initial phase angle is pi by 4, so obviously the angle between the first reference axis or u1t is pi by 4, and this one is the 3 pi by 4, this one is the 7 pi 5 pi by 4, and this one is the 7 pi by 4. Okay, now clear the distance um, between the origin is root over es, eb, root over eb, this one. So this one is the root eb. Okay, so that's why you can see that the coordinate is different, that means the symbol order is different: 0 1 0 0 1 0 1 1. As we want to follow the serial order of coordinate, first, second, third, and fourth coordinate, that's why the sim for first coordinate that will be 0 1, for the second this one is 0 0, for third this one is the 1 0, and this one is the fourth. Okay, so it is a conventional approach, that's why it has been written or expressed like this way. Okay, now coming to the next part, that means we want to know what is the no what is the yeah, we want to know what is the noise immunity or error probability for the case of QPSK. So if we want to calculate the noise immunity, so we want to calculate the distance between two successive bit. So, so we want to calculate, find out, so like this point and this point. So if you want to calculate like this, so obviously it will be like this. So d mean will be 2 TB into PS, that means 2 into root TB. So from the above figure already know that it is already root, this one is the root 2, sorry, root TB. So obviously total distance will be 2 into 2 into root TB. So you can see that this one is the PS into TB, or this one is the EB. So obviously this one is the total distance is 2 into root EB. So which is nothing but similar to the BPSK. So obviously noise immunity for BPSK and QPSK are same. Now next, coming to the generation of QPSK. How can we generate QPSK or QPSK modulator? So this one is the basic block diagram of QPSK modulator. So during the generation of QPSK, we need an polar energy encoder. It is had been written as bipolar, but it should be polar. Okay, so this one will be polar energy encoder. Next, we need an demultiplexer, or you can splitter. You can call it as also splitter, that split the bit into the odd and even part. After that we need two balance modulator or multiplier, and we need two locally generated carrier cos omega ct and sin omega ct. After that we need an adder, and after that we will get the corresponding QPSK. So where, let's see what will happen in case of this structure. So binary data sequence, that means this is the input data. Now we want to convert this input sequence into the polar energy sequence. That means we want to convert for input 1 into +1 and input 0 into -1 volt. Okay, so by using this encoder we convert this input sequence into the polar energy, that means +1 and -1. So you can see that uh, this one is the input sequence 0 1 1 0 1 0 1 1 0 0 1. Then corresponding polar energy pattern will be like this. So for 0 this will be -1, and for 1 +1 +1 -1 +1 -1 plus minus minus 1. Okay, now next part is, next the so BT has been generated, that means it is the polar energized version. Now this has been applied into the demultiplexer, or you can call it as bit splitter. The function of bit splitter or demultiplexer is it separate the odd part and even part, or odd bit and even bit. Okay, so it has been BT has been incoming as serial, but demultiplexer output is sorry, uh, output is in parallel order. That means it has separated out even part and odd part. So you can see that this one is the first, this one is the second. So obviously first bit is odd, second is the even, odd 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 odd, third is the sorry, I mean second, fourth, sixth, eight are the even bit. Now let's see, now we define two signal, or the output of the demultiplexer are two. One is BOT, that means odd bit, another is BET, that is even bit. So BOT, that consists of odd bit part. So here you can see that one is odd, so first bit is minus, so first is minus. Now in this case, first each symbol will last up to 2 TB duration. Okay, so this will be last up to the 2 TB duration. Now next odd bit 1, so this will be 1, but it will last up to 2 TB. Next odd bit 5 for 1, 1 7 1 9 0, you can see that 0. Okay, now let's see the even portion 1 1 4 0 0 6 0, here you can see that 0, and 8 is 1, so obviously here it is 1. 10th 10 is 0, so here is 0. So this is odd number bit sequence, this is an even number of bit sequence. This has been denoted by BOT, and this has been done by BET. Okay, now this, so BOT and BET, now all these output are applied to two multiplier or balance modulator. In case of first odd bit, in case of odd bit sequence, we use root PS sin omega ct as the carrier, whereas in case of second or upper uh, multiplier, we use root PS cos omega ct as the carrier, and output of the second after output of the multiplier are SOT and SET respectively. Okay, so obviously SOT and SCT both are nothing but BPSK signal, but with defined phase. Okay, now if we add them by using adder, the corresponding output of the adder will be nothing but QPSK signal. Okay, so obviously QPSK can be expressed by using this equation: root PS into BOT into sin omega ct plus root PS into BET cos omega ct. Clear? Okay, so this is the block diagram for QPSK generation. Here you can see that this one is the PS cos omega ct, and this is one is the root PS into sin omega ct. And if I multiply PS into sin omega ct to this So obviously Ps into sine omega ct or odd. So first bit is 0, sorry, this one is the odd. So this one is the odd. So first one is the 0. So if we multiply this, as this one is the 0, which is given by -1, so obviously there will be phase shift, or this will be the inverted version. So this portion will be inverted. Next one is the 1, so phase will be inverted like this. So this is nothing but conventional PSK. Okay, and this one is the even portion. So this one is the SET, which is given by where carrier is used as root PS cos omega ct. So for that so 1 no phase shift, that means same carrier, that is same carrier up to this, but here 0, that means phase shift will be happen, and it will be continued up to this, and it will be continued up to this, and again 1, that means again another phase shift, and 0 another phase shift. Okay, so this one is the even part, this one is the odd part, and if we have add them, we get ultimate QPSK. I hope QPSK generation is clear to you. Now coming to the QPSK demodulator. Now following figure shows the block diagram of QPSK demodulator. So this type of QPSK demodulator is synchronous type of detector. So as this is synchronous detector, that means we need to use locally generated carrier. We already know that during the QPSK generation, we have used two carrier. One is sin omega ct and one is cos omega ct. So in the receiver section, initially we need to regenerate this carrier locally. So how can we regenerate them? Basically, we need to extract from BPSK itself. Okay. So in case of QPSK, no frequency has not been deviated or changed, only phase has been changed. So we can easily extract the corresponding frequency. Okay. Now here you can see that this one is the receive signal. Receive signal is denoted by ST. Now this signal has been applied into the a blocks nonlinear block where the signal is raised to the fourth power of it. That means the output of this raised input fourth power is h to the power 40. Okay, so h to the power 40 is nothing but it's consists of different component, like if consists of only omega c, whose frequency is omega c, so st consists of 4 omega c, 2 omega c, omega c, like this. Next we need to use a band pass filter. So the purpose of the band pass filter is to pass the high frequency portion. That means for 4 fc portion we need to only 4 fc portion. So this signal is passing through bpf whose center frequency is 4 fc. That means we get cos 4 2 pi fct or cos 4 omega ct. Okay, next we have used a frequency divider. The purpose of the frequency divider, as from the name suggests, we divide the corresponding frequency of the signal by 4. So we get ultimately the sinusoidal signal whose frequency is the cos 2 pi fct or cos omega ct, but the output of the frequency divider is 2. One is cos omega ct, another is sin omega ct. So basically there is no difference. If we make a 90-degree phase shift, we can get from sin to cos or cos to sin. Okay, so ultimately up by this blocks we can get locally generated carrier. That means that's why we use the term synchronous detector. So we need cos 2 pi fct and sin 2 pi fct. By using raised power section and bandpass filter and frequency divider, we generate cos 2, or we extract cos 2 pi fct and sin 2 pi fct or cos omega ct and sin omega ct from the received signal itself. Okay, now this locally generated carrier has been applied into the two balance modulator. So this one is the upper balance modulator or multiplier, this one is the lower. Lower has been where in the both of the balance modulator the input is st and others carrier as used as cos 2 pi fct and sin 2 pi fct. So here you can see that if we consider only the upper modulator only, so upper multiplier or upper balance modulator only. So for this case, the corresponding output of the modulator will be st into sine 2 pi fct. Okay, now the st into sine 2 pi fct. Now this signal is passing through a integrator. Okay, so after that, the output of the integrator is going to the multiplexer. Now let's see what is the function of the integrator. So now you can see that the input of the upper integrator is st into sine omega ct. So we know that the st is nothing but the ps into b0 t sine omega ct plus ps into bet cos omega ct. So obviously if we multiply it with sine omega ct, we get this type of signal, root ps into bot sine square omega ct plus root ps into bet cos omega ct into sine omega ct. Okay, now the purpose sorry the working principle of the integrator. Now integrator will integrate the incoming signal over the time period Ts equal to 2 TB, as we consider 2 bit for only one symbol or one message. Okay, so we will integrate over Ts into Ts equal to 2 TB. Okay, so the output of the upper integrator is given by 2k plus 1 TB up 2k minus 1 into TB. Okay, you can see the difference between them is already 2 TB. Okay, so k can be given can take any value. Okay, so st into sine omega ct. Fine. So obviously it will be given by it will be expanded like this: bot root ps integration from 2k minus 1 to 2k plus 1 tb into sine square omega ct in dt plus bet root ps integration from 2k minus 1 into tb up to 2k plus 1 into tb cos omega ct sin omega ct dt. Now we need to substitute this. That means we already know that sin square omega ct is nothing but half into 1 minus cos 2 omega ct, and cos omega ct sin omega ct is nothing but half into sin 2 omega ct. Okay, so if you make substitute these two into above equation, so we get this type of equation. So half into bot root ps integration 1 into dt and half bot root ps integration cos 2 omega ct dt and half bet root ps integration sin 2 omega ct dt. And so here you can see that there is two integration that consist of sinusoidal part integration. Now we know that the integration of a sinusoidal signal over complete time period or over its integral number of cycle is nothing but 0. Okay, so output of this two integration is 0, and so the output of the integrator will become only this part, half bot root ps integration 1 into dt. And after that, if we simplify it, we will get half bot root ps into 2 tb, and this is nothing but bot root ps into tb. So obviously the output of the upper multiplier or product modulator is bot ps tb. That means this is the consist of odd bit. Okay, and the similarly you can prove that for the lower integrator, the corresponding output will be bet and pstb, and that root ps and tb is this is nothing but an amplitude. Okay, so this will be nothing to concern about. So we need to concern about that if we get odd bit and even bit separately. So yes, we get the bot and bet separately. Now we need to use multiplex them so that we can get the serial output, as the input sequence is the serially in serial order. So we need to use a multiplexer so that we can get similar type of baseband or original baseband signal. Remember, for each bit stream, multiplexer should hold the bit corresponding bit for TB second, so that we can get the original baseband signal. Now coming to the last part, that is the base bandwidth calculation of QPSK. As you already know that for the QPSK, QPS bit stream has been divided into even and odd bit respectively, and each symbol is in this stream has period of Ts equal to 2 TB. Therefore, the original base, spectrum of the baseband signal is from 0 to FB by 2. Okay, so the bandwidth for this is FB by 2 from this one to this one. Now we have used carrier signal. So as we used product modulator and use cos omega ct or sin omega ct, so obviously the spectrum of the baseband signal will be shifted into the plus minus fc. So we can see that total spectrum will be shifted into plus minus fc, and this one will be the practical bandwidth where the most of the power consists of. So the bandwidth for the corresponding QPSK is fc plus fb2 minus fc minus fb2, that is fb. Interestingly, in case of bpsk the bandwidth is 2 fb, but in case of qpsk the bandwidth is the fb. So obviously bandwidth efficiency is better than qpsk. Sorry, bandwidth efficiency is better for qpsk over bpsk. So there are two advantages: first, bitrate has been increased, and second, bandwidth is less. So these are the two important advantages of QPSK. Now coming to the conclusion part. So in this class we have studied one of the important digital modulation technique, that is quadrature phase shift keying, and we have also observed corresponding waveform where mm, two bits, two successive bits are grouped together, and it is possible to assign four different phase angle for four different message group. So for conventional approach, 0, 90, 27, 180 and 270-degree phase angle are assigned. But another popular approach is pi by 4 QPSK, where pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4 phase angle are used for the different message or different symbol like 000111 or 01. And moreover, after that we have also observed the corresponding signal space diagram and find out the corresponding error probability of error or noise immunity. And after that we also observe the uh, QPSK modulator and demodulator part, and at the end we have find out that bandwidth is FB, which is better than the conventional binary phase shift keying. Okay, so these are the few references that we have used. Thank you.